Hello everyone, welcome to the calculus lecture week 10. So in this lecture, we're going to talk about the first one is point of diminishing return. So this is about at what point the return is diminishing in terms of additional increase in our inputs. And secondly, we have the how to locate the absolute extrema, right? What is absolute extrema and how to locate it. And finally, we're going to talk about the its applications and in particular, how to use calculus to solve for optimization problems. So let's dive in. Okay, now first let's look at the point of diminishing return. So there are a few subjects we are interested in. For example, if you look at the raw function n of x, right, and then we have its first derivative and prime of x and second derivative double prime of x, right? So and we are interested in so this is raw function, and this describes either the raw function is decreasing, increasing or decreasing, right? So it describes the behavior, whether it's increasing or decreasing of the raw function, which is n of x. Now, when it comes to the second derivative, right, the second derivative function, then it also talks about this increase or decreasing of n prime of x, right? So it describes this increase or decreasing of the first derivative function, and it also talks about concavity of the raw function of x, right? So it has both are equivalent. It's just when we look at different levels, different functions, then the interpretation is different. So now, for example, a quantity increases at increasing rates, and then increases at a decreasing rate. So in terms of rate of change, first it increases, and then it decreases. So what does that mean? That means that first, the rate of change, the n prime x, is increasing, then it's decreasing. So that is what it's talking about. So when this happens, the location at which the rate of change goes from increasing to decreasing is called the points of diminishing returns, right? So specifically, we're looking at this point, right? Graphically, we look at this graph. Now, the curve on the bottom is referring to the n prime of x, right? So this is the curve of n prime of x. So first it's increasing, then it's decreasing. So when this happens, we have this point, which is when the n prime of x reaches the local maximum, right? Which is local maximum. Then this point is called the point of diminishing return, right? So because now this is the local maximum of n prime of x. However, there's more information in this graph. So again, this point is the point of diminishing return, and n prime x goes from increasing to decreasing, right? Literally increases and decreases. So corresponding to the raw graph, which is n of x, right? So we have the corresponding point here. And then, so on the left, what we have is that n double prime is actually above 0. So why is that case? Because now if you look at the interpretation, right? So if the first derivative is increasing, then it's actually so what's on the left is concave function, right? So on the left is concave, and on the right is on the left is convex, and the right is concave, or concave downwards. So on the left is concave upwards, right? So when this happens, then this point is also called the inflection point, which we covered earlier. So it's the inflection point of the raw function, which is n of x, right? And now both actually give you the same answer, because now if you look at the second derivative, we do the test. For example, we plug in the number, and then we can use the Sancha methods. We see that it's positive, then it's convex. Plug in any number, then use the Sancha method, is negative, right? So when it's positive, it means that so when double prime of x is positive. Now what this means? It means that so basically it means now for n prime of x, is increasing, right? So for n prime of x is increasing. So that's actually the literal interpretation, which is falls into here, right? So this is our interpretation regarding the real function of double prime, which is a single prime, right? So if it's increasing, then the derivative is positive. So corresponding graphically, if it's increasing, right? So in this range is increasing, then the second derivative is actually positive, right? So that's first level of interpretation. The second level also means that now it is convex, right? Because it's positive, so it's convex. So both interpretations work. They are equivalent. And that's how we interpret the graph. So basically, now other than the inflection points, we now know that this actually, if it is a local maximum of n prime of 1, right? If this happens, then this point is called the point of diminishing return. All right, so let's look at one example where we put it into a bit of practice. So, okay, so here we have a function, and the function is taking this form, and pay attention to the domain. So now what the question asks that what is the rate of change of sales increasing when it's decreasing? So again, the object of the subject of interest is rate of change, right? So that's hinting us that we need to get the form of n prime of x first, right? And then, so with this form, then we also need to have, so to be able to determine which points is the points that's causing this to happen. So first increasing, then decreasing. In other words, we're looking for the point of diminishing returns, right? And then, and basically at this particular points, we have the maximum rate of change of sales, right? So at this point is the maximum rate of change. Now, so to be able to identify that, we need to have access to double prime of x, right? So if we do the derivation, now we know that it's actually the first one will be x squared minus x, right? And the second one is 3x 6 minus 6 minus x. Okay, so this is the form of the first and second derivatives, and now we'll use them to solve for the point of diminishing return. So in other words, we're looking for an inflection point. Now, how do you solve for an inflection point? We just equate this to 0, right? To be able to get us the inflection point, right? And then we want this inflection point to be the case when it is actually a local maximum, right? A local maximum. So it has to be first on the left is positive and the right is negative. So that's it's increasing and then decreasing. Okay, so by equating the second derivative to 0, what we have is x will be equal to 0 or 6, right? So these are the two critical points when we set this to 0. And what we have here is that we can actually draw a graph, and then these 2 points here, so 0, 6, and then pay attention to the domain here. We actually can draw 9 here as well. So because it's the end of the interval. So so this is the graph of now we still live in the space of n double prime of x, right? And we also want to have another graph. Let me just draw it here on the bottom, which is about the okay. So for let me just move it here. So we have the n double prime of x 0, 6, 9. This double prime. And we also want to look at the single prime, which is the first derivative, 0, 6, 9, and then the rho function, right? So these are the only three subjects of interest, and then we can draw them out first, and then see what happens at this particular point. So now when x is equal to 6, right? So at this particular point, what we have here is that n double prime of x will be equal to 0, right? And then we want to know what is the the first derivative, which is the first derivative. What happens to the first derivative? So let me put a question mark here. right? So put a question mark here. And then we actually want to use the analysis based on the second derivative to infer something about the first derivative. So how to do that? Now, let's just plug in a number, right? So we'll plug in a number, and then we see that, for example, x, take the x equal to 3, then this portion, this the expression for the second derivative is going to be positive, right? So on the left is positive, and all about the number in between this and in between, let's say, the second range, then we see that it's actually negative, right? So what this means is that, oh, on the left, it's going to be convex, right? On the right, it's going to be concave. And this point is actually the inflection point, right? If we look at the raw function of f, x, right? And also can look at, so this is from a concavity point of view, concavity. So also look at from the perspective of the first derivative. Now, what's missing is that in between 0 and 6, right? In this first range, the second derivative is positive. That means that the first derivative is going to be increasing, right? It's going to be increasing. And then on the second range is the second derivative is negative, so it's going to be decreasing, right? So this point is the local maximum point of the first derivative, right, of x, right? So that's what we know about the first derivative, and we also from the second derivative we know something about the raw function. So which let me just put here. It's going to be something like this, right? So this is the this inflection point. So not properly drawn to scale. Okay, so this is the inflection point. So that's what we know about the function, and we can actually draw it out. So let me draw the graph out, not to scale. Right, so we have the x, and we have y here. So to be able to draw the graph, we need to have a few points. First one is, what is the intercept, right? So set x equal to 0, then what is the value of y, right? So y will be equal to 200 in this case, right? So it's just 200. Now, this is the points, and also have some points. For example, what is the value of y when it's 6 and 9? So let me just do it out. So when this is 6, this is 9. When x equals 6, x equal to 6, n of x will be equal to, let me see. So if you do the calculation, then it's going to be 5 to 4, right? So it's going to be 5 to 4, which is around here. So this is our second, so it's our one of the critical points. And then when x equal to 9, it's going to be, well, it's going to be another value, which is somewhere around here. So specific values I do not calculate for now. So, okay. Now, what this means that this is actually inflection point. So inflection point, inflection. So that means that on the left, needs to be a convex. So let me draw it a convex curve. And then after this point is concave, right? Concave. So then this makes an inflection point. So this is the curve of n of x. Now, we also want to draw the function for n prime of x, right? So on the left, it's going to be increasing. So let me just get so we can actually get the coordinates of the points, right, for the function n prime of x. Right? So after get coordinates, then we also start from here, right? So get the coordinates of the x-axis, and then it's going to be increasing, right, and then decreasing until we reach this point. Because when x equals to 9, then it's going to be 0. So this is actually the local maximum, right? Maximum of n prime of x, right? Because now on the left is increasing, on the right is decreasing. So based on our previous analysis, so that's how we can analyze the different pieces, right? So we have n of x, the raw function, the first derivative, and the second derivative. So these are different tools we can use to know more about the behavior of a function. All right. So let's move on. So first, we have the absolutes, maxima and minima. Now, what this means is that we can actually look at a curve, right? So for example, this is a curve. Now, there was no absolute maximum minima because it's actually x can go to negative infinity, and on this side I can go to positive infinity. So it cannot find the absolute, the only maximum or minimum, right? However, there are some other cases we can find. So for example, in the second curve, now this point, so this point is the absolute maximum across the whole range, right? Across the whole range. And then also the same thing, this is the absolute minimum across the whole range. So so basically what it says that the absolute maximum is the point that across the whole range, it is above any value in the whole range, right? So that's called the biggest number within the whole range, and then also correspondingly the smallest number, which is also called absolute extrema, x and minimum in the whole range. So both are together called absolute extrema. Okay, so and on this we have the extreme value theory, which is good to know. So what this means is that if the function is continuous, right, and on a closed interval, so any interval, for example, if you look at any interval here, and we can draw just any curve, right? Any curve that's continuous means that we can draw it without lifting our pen, right? And then what this theorem says is that it has both an absolute maximum and absolute minimum on that interval, right? So which is intuitive because now with this range, you can draw, for example, draw this function which is continuous. Then this is our absolute maximum. This is our minimum. This is our absolute maximum, right? So if we take on adding the range, then it's also the same case. So either this is a point of maximum, and then this is point of minimum, right? And then different cases depending on. So basically, there are few candidates. So first candidate is the local maximum or minimum. So this is local maximum, this is local minimum. And then second type of candidates is the endpoints, right? Endpoints. So if we just list out all these candidates and then compare them together, then we can get the candidates for the global, or also called absolute maximum or the minimum. All right, so let's look at one example where we put it in practice. So here we have one interval, right? And then we are asked to solve to find the absolute maximum and the minimum, right? So how to go about it? Now we can just follow the procedure, which is that we actually want to get f prime of x first, set to 0, right? To get us the candidates for the critical points, right? So critical numbers, right? Critical numbers, what is the value of x? And then, so this is the first type of candidates. So candidates. And we have the range, the endpoints, 0, 6, 4. So these two are also candidates. Then with these two type of candidates, we compare them together, and then we can see what is the biggest or the smallest value out of this. So procedure-wise, we check that. Okay, first we need to check if it's continuous, right? So this only works if it's continuous. Because the function is polynomial, then it's actually continuous everywhere. And then we find the critical numbers, right? Of course, interval, and then the endpoints. So this is the first type of candidates, and then second type of candidates. And then we just compare them together to get absolute maximum and minimum. All right. So now let's look at the second derivative and extrema. So this is already something we covered earlier, which is that what it means to have derivative, the second derivative that is always positive. Okay, so that is positive at this particular point when x equal to c. That means that at this point, it is actually convex, right? So this is convex case, and then this concave case. So when this happens, then at this particular point, this is called local minimum, right? It's local. And on the second case, it's called local maximum, right? So so basically, this is a utility rule we can use. So for example, to identify whether this is maximum or minimum, right? We can just use the second derivative and check the sign, right? Check the sign. So check the sign. And in both cases, the first derivative is all zero, right? Because we need to say it's actually the slope is zero. However, when the second derivative is zero, right, and that is well, it's a bit obscure, then we cannot make any conclusion for that. We still need to reason about what's the function look like in terms of graphically, and then see how it goes. Okay, so that's for the second derivative and the use of the second derivative to find extrema. Now, okay, last point I want to mention before we end this video is that we have the second derivative test for locating the extrema points. Also, what it means is that now if at this point it is zero, and then the second derivative, the first derivative is zero, second derivative is positive, then this is the absolute minimum. So, which is basically what we covered in the previous slide, right? And then there's only one critical number in this range. So this is the condition we need to enforce, right? So because now this makes it sort of like strictly convex or concave, right? So it's not like something like this. It's actually can only be like this or like this. So this is called a strict convex or concave. And then correspondingly, if again we have this point where the first derivative is zero, second derivative is negative, then this point is called the absolute maximum, right, which is this point. So, all right, and that's it for this video. And let me just look at the. Okay, so basically we can argue about the same thing by checking out the first derivative, second derivative, and then use this test to perhaps identify what is the maximum or the minimum in terms of local behavior. Okay, so thanks for watching, and I'll see you in the next video.